Okay, so for those of you watching online, the mic was just muted. I'm going to start over. So today we're going to have our first lecture on reinforcement learning algorithms that try to optimize reward functions. And we'll go into a lot more detail in subsequent weeks about the particular algorithms themselves, and we'll go into a lot more detail, a lot more derivations. Today, really, the goal is to get a high-level overview of the general definitions in reinforcement learning, the broad classes of algorithms, and kind of a high-level view of the anatomy of the typical reinforcement learning algorithm. So things will be a little bit more high-level, and if they seem a little vague here, don't worry, we'll go into a lot more detail in subsequent weeks and really cover all the intricacies of how these methods are derived and how they can be implemented. Okay, so a few logistical notes first to start with. Homework 1 is due next Wednesday, so hopefully all of you have gotten started on that homework. If you haven't, do make sure to get started on that soon. If you have any trouble with homework 1, make sure you go into the GSI's office hours. Remember also that Monday is a holiday, so please plan ahead as far as office hours and so on. Remember to start forming final project groups. So at this point, I believe we've already released the final project assignment. If we haven't, it'll be out very, very soon. So that should give you a little more of the details. But the important thing right now is project groups, 1, 2, or 3 people. You don't have to work in a group, but you can. Generally, we found in the past that groups of 2 work well, but you're welcome to have groups of 3. If you want to have groups larger than 3, please come into office hours and just ask the GSIs or me to make sure that the scope of your project is sufficient for that. But we expect most groups to be 1, 2, or 3. And there's also like a little document that we put that's available on Piazza, or that we will put there soon, that basically describes a few potential ideas for final projects. Most students in past years have done their own kind of ideas, but if you want a document with it to sort of give you a few ideas, or maybe suggest some directions you can think about, you can check out that document. But generally, we expect most people to just come up with their own stuff and do whatever you want, but you're also welcome to do one of the things in that document if you would like. All right, today's lecture. So today I'm going to go through the definition for a Markov decision process, which is sort of the fundamental mathematical object that lies at the heart of most reinforcement learning algorithms. I'm going to define the reinforcement learning problem. So the reinforcement learning problem is an optimization problem, but you need to define what it is that you're optimizing and with respect to what. And then I'll go through kind of the outline of a typical reinforcement learning algorithm. And actually, all of the algorithms that we'll cover in this class, they can basically be broken up into 3 parts. And I'll talk about what those parts are and give a few examples of how those parts might be instantiated for different methods. And then I'll give a brief overview of the different types of R algorithms that we'll cover in this course. So the goals for today's lecture will be to understand the definitions and the notations, to understand the underlying reinforcement learning objective. What is it that reinforcement learning algorithms are trying to optimize? And get a summary of the kinds of algorithms that we might have there. And we'll, of course, go into more detail about each of those algorithms in subsequent lectures. Okay, so let's start with definitions. We already saw many of the components of a sequential decision-making problem in the imitation learning lecture. So we talked about how a sequential decision-making problem involves observations, actions, a policy, which gives you a distribution over actions given the observations. The policy is typically what you're trying to get. And a policy is it can be parameterized in some way. So in the imitation learning lectures, we talked about a policy parameterized by a parameter vector theta, which represents the weights in a deep network, which models the conditional distribution over A given O. We'll also see that in some reinforcement learning algorithms, instead of learning a policy directly, you learn some other kind of function, such as a value function or a Q function, from which you can derive a policy. So you're not always directly learning policies like this, but sometimes you are. And actually, in the first class of reinforcement learning algorithms that we'll cover next week, which are policy gradient methods, you do directly learn an object of this form. But that's not in general always the case. Now, in the most general kind of view of reinforcement learning, your policies give you actions conditioned on observations. You can also have a fully observed setting where your policies give you actions conditioned on states. And the distinction between states and observations is something we discussed last time, which is that states satisfy the Markov property, meaning that state 3 is conditionally independent of state 1 given state 2, but observations in general do not satisfy the Markov property. And this distinction between fully observed and partially observed settings is important for some algorithms. So some algorithms assume that you're in a fully observed setting. Some algorithms are perfectly happy to deal with partially observed settings. So there's an important distinction to be conscious of. OK, so in imitation learning, we had this example, maybe something a little more concrete, like driving, where you would collect a bunch of data from a human expert. And that data consists of the observations that the expert saw and the actions that they took at those time steps. You would collect your training set made up of these observation action tuples, and then you would use some standard supervised learning algorithm to train a network that maps from these observations to actions. And more generally, you could do something a little more elaborate like Dagger, which tries to address some of the shortcomings of the standard behavior cloning approach. OK, so now let's get away from the imitation learning setting. Let's talk about how we can actually learn effective policies in cases where we don't have expert data. So we talked at the end of the imitation learning lecture about how at this point you would need to actually define what it is that you want your policy to do, since you don't have data anymore to illustrate this, and you would do this with a reward function. So the reward function basically is how we're going to be able to figure out which actions are better or worse. The reward function in general is a function of states and actions, and it tells us which states and actions are better. But the critical thing is that we're not trying to maximize the reward by choosing the best action right now. We're trying to maximize the reward over all time, which might mean that right now we might choose an action that is less rewarding so that we can reach a more rewarding state later on. So to kind of build on this little driving example, maybe you have a setting where you have high reward when the car is happily driving on the road, and low reward when the car is colliding with another car. But of course, there's a sequence of events that led up to this low reward event, which themselves don't have low rewards. So maybe you get pretty high reward for driving fast, you get high reward for driving fast through the middle of an intersection, but you get low reward when you do so and hit another car. So you might choose to avoid driving fast through intersections because you know that it might sometimes lead later on to states with low reward like this. So the important thing, and a big part of the challenge in reinforcement learning, is that you want to optimize your reward over all time, which might mean doing things in the near term that have low reward so you can get high reward later. So all these things that we've introduced so far, the state, the action, the reward, the transition probabilities, all together, they define what's called a Markov decision process. So a Markov decision process is basically the definition of the world in reinforcement learning. So it has states, actions, rewards, and transitions. And many of you probably heard the term Markov decision process before. If you took an undergraduate artificial intelligence class, you might have heard this term. And maybe you might be wondering, well, who the heck is this Markov guy, and why does he have a decision process? So this is Andrei Markov, and he didn't invent the Markov decision process, but he did do a lot of work on stochastic processes and is best known actually for Markov chains, which are not Markov decision processes. So Markov chains are a very simple model for a temporal process, not a controlled temporal process, just a temporal process consisting only of states. So in a Markov chain, you can define it with just two objects, a state space and a transition probability. So S is the state space, and this is a set of states that's either discrete or continuous, whatever you want. And T is the transition operator. So the transition operator defines the probability of entering a particular state given the state that you're currently in. So it's just a conditional probability distribution. And the reason that we call this thing a transition operator sometimes is that in discrete state spaces, you can actually express this T with a matrix, and then it acts as an operator on vectors of probabilities. So to put this into a kind of more formal notation, if I define mu t comma I to be the probability that I am in state I at time step t, then I can create a vector mu t, which is where basically every entry in that vector is the probability that I'm in the corresponding state at that time step. So if I have like 5 states, then mu t is a vector of 5 numbers that all sum up to 1 and are greater than 0. So that's my state distribution. And then if I create a matrix where Tij is the probability that I'll transition to state I, given that I'm currently in state j, then I can simulate my Markov chain forward with a simple linear equation. I can just say that mu t plus 1 is equal to t times mu t. Because when I multiply this vector by this matrix, I'm putting things over here that are the probability that I was in that state before, and I'm getting the probability that I am in each state now. So if I want to simulate the Markov chain forward, if I have a discrete state space, then all I do is I multiply my current vector of probabilities by the transition operator, and I get my new vector of probabilities. And you can imagine that in continuous spaces, all the same stuff holds, it's just that now my vector is infinite dimensional, so it's a little difficult to cram into a computer. But the basic theory stays exactly the same. OK, and we can graphically illustrate a Markov chain. Very, very simple. The only variables in the Markov chain are states, and the only conditional probability distribution is the probability of the next state given the current state. So everything in the world of Markov chains is simple and straightforward. And of course, in the Markov chain, the states satisfy the Markov property, which is to say that the next state is conditionally independent of the previous one given the present. OK, so now we can take the Markov chain and we can turn it into a Markov decision process by introducing some actions and some rewards. So a lot of this kind of originated in the world of dynamic programming with Richard Bellman and company in the 1950s. So in the Markov decision process, we add two additional things. We still have our state and our transition operator. Now we're going to add an action space and a reward function. So we have our state space, which is still a set, a discrete or continuous of states. We have our action space, which is again a set that can be either discrete or continuous, a different set. And now our graphical model looks like this. So now we've added these actions. The actions don't depend on each other, but they do determine the next state together with the previous state. And our transition operator is now a tensor, because the transition operator needs to express probabilities of states given states and actions. So we still have our mu t, which is the probability in a particular state at time step t. You can also have another vector, which is the probability that you take a particular action at time step t. And now your transition operator is a tensor with 3 dimensions. So Tijk is equal to the probability you go into state I, given that you were previously in state j and took action k. And then you can again express the simulation of this process forward in time as a linear operation, linear in mu, and linear in the action distribution, and linear in the transition operator. So this is basically just the equation for applying that transition operator, just a big summation. OK, so everything, again, is actually quite straightforward. Now you still have to put in this reward function, and the reward function, as I mentioned before, is just a scalar valued function on the cross product of states and actions. So over all states and actions, over all combination of states and actions, you have a scalar field which defines your reward function. And that's the only other thing you need to fully define your Markov decision process. Now, we didn't talk yet about observations, and I mentioned before that in the most general setting for reinforcement learning, you also have observations in addition to states, and your policy might have to choose how to act entirely based on those observations without knowing what the states are. So if we also include observations, we get something called a partially observed Markov decision process, which is a generalization of Markov decision processes that gives us the most general form of the reinforcement learning problem. We won't always work with partially observed Markov decision processes. In fact, many of the algorithms that I'll derive in subsequent lectures will deal just with regular MDPs. But in the most general case, you have partially observed MDPs. So in POMDPs, partially observed MDPs, you also add an observation space and an emission probability. These are the only 2 additional things we're going to add. So we still have a state space, which is discrete or continuous. We have an action space, which again is discrete or continuous. And we have an observation space, which can also be discrete or continuous. So maybe the state space is the position and momentum of your car. The action space is whether you're hitting the brake or the gas or turning the steering wheel. And the observation space might be images from your camera. So if we draw the corresponding graphical model, it looks like this. So all we've done is we've added these observations O, which are condition on S. We still have our transition operator, exactly the same as before. So the transition operator doesn't touch the observations. But now we also have an emission probability. And an emission probability is just a probability of OT given ST. So again, it can be expressed as a matrix. And we have our reward function just like before, which, just like before, is a scalar field on states and actions. OK, so at this point, does anyone have any questions about MDPs or POMDPs or any of the definitions so far? OK. So now that we've defined POMDPs and MDPs, we can actually define an objective function for reinforcement learning. We can actually write down in an equation what it is that we want a reinforcement learning algorithm to do. So we're going to have our policy. And the policy might be represented either explicitly as a neural network or in some implicit way via a value function. We don't really need to worry about that too much. The main thing we need to take note of here, OK, we'll come back to partially observed later. We'll just say it's conditional on states. The main thing we want to take note of here is that whatever way we have of representing our policy, it has some parameters theta. So if we're representing a policy explicitly as a neural net that gives A given S, theta corresponds to the weights in that neural net. But in general, it's just some vector of parameters. So theta is what you're trying to learn. The state goes into this thing, the action comes out, and both the state and the action affect the world, which produces the next state. So there's some distribution over the next state given the current state in action, some kind of transition operator, which you in general wouldn't know in advance, which determines the next state. So that's the graphical illustration of the process. And this process gives rise to a probability distribution over trajectories, over sequences. So a trajectory is a sequence of states and actions. Here I have it written out as a finite length trajectory with length capital T, but we can also have infinite length trajectories. But for now, let's deal with finite length because it's a little easier to write down the objective this way. And with all the things that we've defined, we can actually write down an equation for the probability of seeing a sequence of states and actions, a trajectory, S1, A1, S2, A2, et cetera, until you get to ST, AT. And for shorthand, I'll often abbreviate this as P of tau. Tau just denotes a sequence of states and actions for a particular parameter vector theta. We can write this down as, just via the chain rule, as the product of the probability of S1, this is your initial state probability, the probability you start in a particular state, times a big product over the probability of taking the action AT in state ST, and the probability of transitioning to ST plus 1 given ST-AT. So this just comes from the chain rule. So this gives us a distribution over trajectories. And now we're going to define our objective using this distribution. So our objective is to find the parameter vector theta star, which is the argmax of the expectation under the trajectory distribution induced by theta of the total reward over that trajectory. So you have to write it as an expectation because, in general, the states and actions that you'll see for a particular parameter vector are random variables. And you have to take the sum of rewards in expectation under the distribution over those random variables, which is induced by the parameter vector theta, which affects this conditional probability distribution in your model. So this is the reinforcement learning objective. Now, in many reinforcement learning problems, we might not even know what P of ST plus 1 given ST-AT is. So we can write down this objective on a piece of paper. We can't necessarily always perfectly evaluate it in a computer. And we'll talk later about how we can approximate it in various ways. OK, so now we can break down this objective a little bit more and also derive an objective for infinite horizons. If we recognize that this probability distribution actually describes a Markov chain, but a Markov chain with a different state. So if we construct a new state, which consists of a concatenation of the state and the action, this whole thing actually defines a regular, good old-fashioned simple Markov chain on S, comma A. So this is our graphical model for our MDP. It has states and actions. And we have a transition probability, the probability of ST plus 1 given ST, comma AT, and we have the probability of the action given ST. So we can equivalently turn this into a Markov chain over now ST and AT together, where the transition probability, the probability of going from STAT to ST plus 1, AT plus 1, is just given by multiplying together the transition probability and the policy. This might seem like kind of a silly exercise, but the reason that this can be useful is that we know very well how to analyze Markov chains. We know how to find their stationary distributions and all these other things. So the same concepts that we can use to analyze Markov chains can be applied to Markov decision processes. So let's take the finite horizon case, the one we had before. This is the objective that I had on the preceding slide. And we can do a few things with this objective. For example, we can write it out as a sum of expectations over state action marginals. We can take actually the sum outside of the expectation and simplify things a little bit. So remember, this is a Markov chain where the transition probability is the product of the transition probability in the MDP times the policy. We can take the sum outside of the expectation just by linearity of expectation. And now the thing inside the sum, the reward, depends only on the state in action at that time step, which means that we can simplify it to say, well, this is just going to be the sum of expectations over probabilities of ST comma AT. So this is a marginal distribution. It's obtained by marginalizing out all the other states and actions that are not at that time step. So in Markov chains, you can actually compute these marginal distributions. It turns out to be pretty straightforward. You can simply simulate a forward, for example. In practice, when you don't know the transition operator, of course, things get more complex, and we'll cover that later on. But at least we can define and redefine the objective like this, which is a little simpler. It's now a sum over time of the expected reward at that time step. So this is called the state action marginal. This state action, redefining things in the state action marginal way is not actually like all that useful right now. But one of the things that it lets us do, which is very useful, is derive an objective for reinforcement learning in the infinite horizon case. So in the infinite horizon case, it might seem a little perplexing how you can possibly have something like this because the sum over an infinite number of terms. So what if t equals infinity? But you can actually get a well-defined objective here because in a Markov chain, under some mild assumptions, you can derive a stationary distribution. You say if it's simulated forward infinitely far, eventually it settles to a particular distribution over the states. So how can we do this? Well, this is the equation that I had before that when I explained how t acts as a transition operator. So if you have t, you can get ST plus 1, AT plus 1 just by multiplying the current STAT by t. So this is the state action transition operator. And remember, this is obtained by multiplying together the MDP transition operator by the policy. And in general, if you want to simulate a forward k steps, all you have to do is hit your current STAT by your transition operator raised to the power k. So you basically do it k times. If you want to simulate forward an infinite number of steps, multiply it an infinite number of times. So we can ask this question, does this converge to a stationary distribution, meaning that if k is large enough, do you eventually get the same value for this thing over here? And we can try to derive what such a stationary distribution might look like. So stationary distribution means that once you take your vector of probabilities and you hit it with t, you should get back the same vector of probabilities. Because that means that your distribution is not changing anymore. That doesn't mean your state is not changing. So you might be moving around to different states, but on average, your distribution remains the same. So what we can do is we can simply take this thing and we can solve this system of equations. So stationary means you have the same distribution before and after the transition. Solve the system of equations. This is identity times mu is equal to t times mu, so you can have t minus identity times mu is equal to 0. And from this, you can recognize this as an eigenvector problem. So mu is the eigenvector of t with eigenvalue 1. Now you can ask, well, does t actually have an eigenvector with eigenvalue 1? The answer is that it always does under some mild regularity conditions. So one condition that you need is ergodicity, which means that you can always come back to any place that you came from. So if you have dead ends in your MDP, this might not hold. Or if your MDP is sort of split into two halves, where you can never go from one half to the other. But in general, if you can come back to any place where you started, then you're going to have this property that the stationary distribution will exist, which means that you'll have an eigenvector with eigenvalue 1. And that means that you can define a stationary distribution. You can say that if I'm going to transition enough times, eventually I will settle into some distribution, I will remain in that distribution forever. So we're going to call that distribution p theta s comma a without putting a t subscript on there, just to indicate that this is where you're going to settle in after you run it forward long enough. And now you can actually define an infinite horizon objective. We don't want to have a sum that goes to infinity, so we're going to slightly change it by putting a 1 over t here. Question?
Yeah, so about the stationary distribution thing, I guess in the real world, like usually like if you get stuck in some state, it's not possible to return, like say, like the robot just breaks down or something.
Yeah, so the question was, okay, ergodicity sounds nice, but is the real world actually ergodic? Like if you're controlling a robot and one of the states is the robot is broken and the robot never gets unbroken and never gets fixed, that seems like a problem. And yes, it is a problem. So a lot of analysis of MDPs, especially in the infinite horizon case, will assume ergodicity. In the real world, ergodicity often doesn't hold, which causes a little bit of a glitch for some of these things. In practice, you can still sort of derive the right thing with ergodicity and then hope for the best, and that's what everybody really does. But it's a really good point that in practice, there are many, many cases where ergodicity does not hold. Okay. So now if we want to go and define an infinite horizon objective, okay, the first thing we notice, that's a sum of capital T terms. So if capital T goes to infinity, and your rewards, let's say, are always positive, this thing can go to infinity too. So you put a 1 over T in front. Dividing by a constant doesn't change the optimum, so it's okay to put that 1 over T. And it will give you a finite number. This is sometimes referred to as the average reward objective. There are also other ways to get a well-defined objective that is not infinite without dividing by t, but this is a very simple way to do it. And now, let's see what happens as t goes to infinity. As t goes to infinity, almost all terms in your sum will be this stationary distribution. So that means that this expectation will go to expectation under the stationary distribution of the reward. Right? Because, well, let's say that you ran this for like 1,000,000 steps. Maybe the first 1,000 steps were kind of weird, but then it settles into the stationary distribution. Well, run it for, you know, another 1,000,000 steps, and then even more of that sum consists of the stationary distribution expectations. Run for another 1,000,000, and so on, until eventually it converges to this thing in the limit of infinite steps. So now that's how you can define an objective for the infinite horizon case. It's just the expected reward under the stationary distribution of the Markov chain that we get by concatenating the state and action from the Markov decision process. Okay, does anybody have any questions about the infinite horizon objective? Yes?
It seems that with the infinite horizon, we can optimize for the likelihood that we get to some state that we want, but we lose how quickly we get there. Is that?
Well, it depends on your, so the question is, it seems like we're optimizing for reaching some kind of state, but we don't really care how quickly we get there. It depends on your choice of reward. So let's say that I would like let's say my MDP consists of locations in like a 2D world, maybe like where I am in this building, and I'd like to be in this lecture hall, and I want to get there as soon as possible. What I can do is I can define a reward function that is -1 in every single state except for this lecture hall where it is plus 1,000. So then I'll be strongly incentivized not only to get to this lecture hall, but to get there quickly because I incur a reward of -1 for every time step when I'm somewhere else. So based on the choice of reward, you can still get this effect that you describe even with the infinite horizon setting. Okay, in the limit as t goes to infinity, right? Okay, there's a little point that I wanted to make about these objectives, which it's kind of an intuitive point, but it might be a little bit non-obvious just from looking at these things and based on kind of prior knowledge of optimization. Both of these objectives, whether you're in the infinite horizon case or in the finite horizon case, are the expectation of some function. And what you're optimizing is a vector of parameters that affect the distribution under which the expectation is taken. What this means is that it's actually quite straightforward for reinforcement learning algorithms to optimize reward functions that are themselves not differentiable and not smooth, because you're taking the expectation of those reward functions under some distribution. Let me just give an example. let's say that you're driving this car, and you get a reward of +1 when you're on the road, and -1 when you fall off the cliff. Now, if you, let's say, try to set up an optimization problem where you're directly optimizing the steering commands with respect to this reward function without worrying about distributions or expectations or anything like that, you might say, well, this is a really bad optimization problem because it's discontinuous. You go directly from +1 to -1, and there's this big cliff, and all the gradient-based stuff that we know is not going to work here. But in RL, you're always optimizing this thing in expectation. And when you take expectations, even of non-smooth functions, you can often actually get smooth functions after the expectation operator. So let's say that this is not actually an MDP. This is just like a little made-up example. Let's say that you just have some parameter that directly controls your probability of falling. So you either fall or you don't fall. It's either true or false. And you get to pick theta, which is the probability of falling. Okay, you can say just set theta to 0, which is fine. But let's say we want to optimize theta with some gradient-based thing. Gradient-based optimizers require good, smooth functions to optimize. So your probability of falling is theta. Your reward that you get is not smooth. It's like +1 if you don't fall and -1 if you do fall. So that's a really nasty thing to optimize directly with respect to falling. But if you want to optimize it with respect to the probability of falling, it's actually very straightforward, because the expectation of this reward under this probability distribution is smooth in theta. Right? The expectation just has two terms, +1 times this probability being, this event being 0, -1 times this probability being 1, and in theta it's actually smooth. In fact, it's actually linear in theta. So the only point I want to make here is that just because you have objectives, reward functions, that are not smooth, that are discontinuous, that are really nasty, doesn't mean that the resulting reinforcement learning problem is not smooth, because reinforcement learning almost always cares about expectations. And expectations of non-smooth discontinuous functions under nice, well-behaved probability distributions can actually be smooth and oftentimes are. So this is why we can do things like gradient-based optimization in RL, even when we have really complicated non-differentiable reward functions. And in fact, next week, we'll see an example of a reinforcement learning algorithm called policy gradient that does do gradient-based optimization and can be applied to non-smooth reward functions. OK, now let's start talking a little bit about algorithms. So for pretty much every algorithm that I'll cover in this course, it can, broadly speaking, be broken down into 3 parts. So the first part is going to be, I'm going to always draw it in orange, it's going to be to generate samples. So interact with the world, collect data. We had this in Dagger too. So in Dagger, you would interact with the world to collect data that you could then relabel. So in pretty much every reinforcement learning algorithm, we'll have a step like this. Then we're going to have this green step, which is going to be to fit a model or estimate the return. So this green step is not actually trying to make your policy better in any way. It's trying to analyze these samples that you collected here to learn something about what happened. And then you're going to have a policy improvement step where you will use whatever it is that you did over here to get a better policy. And then you repeat. So pretty much every algorithm will have this anatomy, although in some cases, one of these steps might be really, really simple. So let's look at a few examples. And these examples are going to be pretty high level, so don't worry about the details too much. Of course, I haven't actually explained these algorithms in detail yet, so they'll be a little vague, but we can hopefully get the idea of how these 3 pieces might work. So let's look at a simple example of an algorithm that learns by trial and error. This is actually going to be going to turn out to be exactly the policy gradient algorithm that we'll cover next week, but for now we don't really care about its details, we just care about how it works at a schematic level. So what this algorithm is going to do is it's going to generate some rollouts by running the policy. So that's the orange box. That just means you run your policy in the real world or in your simulator or whatever and just see what it does. What does it do? Well, it generates trajectories. So let's say here I ran the policy 3 times. I got 3 trajectories. So that's the orange box. And now these trajectories have different rewards. Some of them are good and some of them are bad. So what my algorithm is going to do is it's going to compute the reward of each trajectory, and then it will try to just make the good trajectories more likely and the bad trajectories less likely. It's just literally trial and error formalized as an RL algorithm. So if this is your distribution over trajectories, that's why you got these three, because these three are actually pretty likely. And if this one, this green check mark is a really good one, and this red X is a really bad one, what you want to do is you want to raise the probability of the good one and lower the probability of the bad one. So it's a trial and error type algorithm. So one of the ways we can do that, which we'll derive in detail next week, is you can say, well, my green box, this is basically the box that tries to analyze what the heck happened when I generated the sample. All it has to do is it has to estimate my objective, which is the expected reward. So it's going to compute the reward function of each trajectory by summing over time, and that'll give me my objective j theta. And the blue box, which improves the policy, will compute the gradient of that objective. So this is an example where the green box is trivially simple. It's just basically a summation. And all the action happens in the blue box. So this is called policy gradient, and we'll derive it in detail next week. Here I just wanted to give an example of how it fits into the schematic. You can imagine a very different RL algorithm where these steps actually are still there, but now the green step is going to be much more complicated. So next, let me tell you a little bit about a model-based RL example. So maybe now, instead of trying to do trial and error, I want to actually figure out how the heck the world works. I want to learn a function, which I'm going to call f phi, that tries to predict the next state. And if I can learn to predict the next state, maybe I can use that to improve my policy. So this is sometimes called model-based reinforcement learning. So here I'm going to learn a completely separate model that takes in states and actions and predicts the next state. And that's what I'm going to do in the green box. So I'm going to still generate samples, and then instead of using those samples to try to do trial and error learning, I'll actually use those samples to fit this f phi so that it can do a better job of predicting the next state. Then in the blue box, what I could do is I could actually backprop through f phi and through the reward to update my policy. In this simple example, the policy is actually deterministic and the f phi is deterministic, so this wouldn't work well in stochastic environments. But if I have a deterministic environment and I know my reward and I can fit my f phi, then I can use this procedure. So it's a very different procedure in terms of the particular details of these pieces, but the pieces are the same. I generate some samples because I need some data. I fit some kind of model, which might just be calculating the reward, or it might be something as complicated as estimating these dynamics. And then in the blue box, I'm going to use that somehow to get a better policy. Maybe I just do it by directly taking the gradient of my rewards, or I do it like here by backpropping through time, through f phi, and through r to get a better policy. But the high-level structure is the same. Yes?
So you can actually observe, like when you know the environment so well that you know what state will come out of, when you actually know the function, is it not necessary to do the model-based RL?
So we'll actually have a lecture on this later on in the course. If you know, like this thing, this f, then you don't need to actually generate any samples. You can just optimize your policy directly through f. And this is what basically the field of optimal control is typically concerned with. And we'll actually talk about a few optimal control and trajectory optimization algorithms later in the course. The reason that it's relevant for this class is that that's basically this blue box in an RL algorithm. So in an RL algorithm, if you don't know f in advance, you can collect samples, fit f, and then use your favorite control or trajectory optimization or planning algorithm in the blue box. So we'll talk about some of those algorithms, but they're generally considered sort of a component of a model-based RL procedure.
Questions?
Yeah.
Where do you get the reward from the first step or the second step?
It depends on your assumptions. So when we cover model-based RL later, we'll actually talk about how in some cases you might assume that you know the reward function, and in some cases you don't. If you don't know it, then you have to learn it up here also. Okay, let me make this RL by backprop example a little bit more explicit. I should say this is not a very good algorithm. In fact, you should probably never actually do this. We'll discuss why later on. But I want to explain it because it's just a really simple example, and those of you that are familiar with recurrent neural nets and backprop through time would immediately recognize what's going on here. So it seems like a simple way just to introduce the concept. So this is basically just a graphical illustration of what's going on here. We have this f that we learned, which is a network that takes in s and a and gives us st+1. And we'd like to improve our pi, which takes in s and gives us a. So if we want to actually implement this thing for some reason, this is the computation graph that it corresponds to. So you have this block, which is what you're trying to learn. this block which you've fitted up here, and then you have your reward, which let's just assume it's known for a second, but you could also learn that. Optimizing pi just corresponds to backpropagating the gradients that will maximize these nodes up here. So that's just backpropagation through time, just like in recurrent neural networks, where the optimization is just trying to make these numbers as big as possible. So coming back to these three blocks, collecting data, that's the orange block. Updating the model F, which just trains these things by themselves without backprop through time, that's the green block. And then updating the policy with backprop through this whole thing, that's the blue block. So not an RL algorithm we would actually often use, but still fits neatly into this framework, and actually we can derive better versions of this to do model-based RL, and we'll talk about that later on. Okay, so most methods will have these three parts. Which parts are expensive and when? Like, was there a question? Okay. Which parts are expensive and when? What do we have to kind of worry about here? So this depends a lot on the particular problem you're solving, how you set it up, and which algorithm you use. So for example, this orange block sometimes might be very, very expensive. So if you're running RL on a real robot or car or power grid or whatever, some kind of real physical system, this orange block might actually be a cause of some concern, because you're collecting data at real time, like until we invent time travel or something, so you're limited by the speed of the universe, essentially. And if you need to collect a lot of data, this orange block might be very expensive for you. If you're training in simulation, like for example, using the MuJoCo simulator that all of you used in homework 1, maybe you don't worry about this block very much, because if your simulator is very fast, you don't really care. It runs at like 10,000x real time, and this block is just not worth worrying about, and you're mainly concerned about the other two. So it depends on your problem. So in this setting, it's a big problem. In the other setting, it's not a big problem. The green block, fitting a model or estimating the return. If we're doing that trial and error learning thing that I talked about before, which is actually called policy gradient, then this green block is very simple. You just sum together a bunch of numbers. It's so trivial, it's like one line in Python. But if you're doing the model-based thing, maybe you're actually fitting a whole other neural network to predict ST+1, this green block might actually be quite important and quite expensive. So you might need to work hard at optimizing it, make sure that, that it converges and does its job, and so on. So that also depends on the algorithm. And again, the blue block, for something like the trial and error learning, you have to compute this gradient and apply the gradient, which is a little more involved than we had up here, but still pretty simple. For the model-based thing, maybe it's a bit more complex because you have to do this complicated backprop thing. So it depends on particulars of the algorithm. And just to wrap up the story with this funny backprop thing, it's pretty simple. Just to be explicit about why it's not good enough. Well, it only handles deterministic systems, as I drew it here. It only handles deterministic policies. And since you're computing gradients through all of this stuff, it only handles continuous states and actions, because you can't compute a gradient with respect to a discrete state. And it actually turns out to be a very difficult optimization problem, because you're doing backprop through time for a huge number of time steps, so you get pretty bad exploding or vanishing gradients. So we'll talk more about these issues later on when we talk about model-based RL. But maybe the thing that I want to focus on a little bit now is this issue with deterministic dynamics and deterministic policies. So I talked before about how in RL usually we're concerned with expectations. And it seems like if we're thinking about things in terms of backprop, then expectations are kind of difficult to deal with because everything is deterministic. So we need to introduce a few tools that will help us deal with optimization problems that involve expectations. So how can we work with stochastic systems? So one really useful thing is to break down the reinforcement learning objective in terms of nested conditional expectations. And that'll actually give rise to things called value functions and Q functions that are very, very useful in RL. So this is our general kind of reinforcement learning objective that I had before, which is the sum over all your time steps. This is the finite horizon version. The sum over time steps of the expectation under the marginal of that time step of the reward. And you can rewrite this in terms of conditional expectations. So we have an outer expectation, which is not conditional, over the initial state. Inside of that, we have an expectation over the initial action, which is distributed according to pi a given s, and it's conditioned on s, on S1, right? So this thing is now a conditional expectation conditioned on S1. The reason there's so much white space here is because I'm going to put a bunch of other things in there. So now we have our first conditional expectation. And once we have this conditional expectation, now we can put the reward at the first time step inside that conditional expectation, because now we have all the variables we need. We have S1 and A1. So now we have this term. But then there's the whole rest of the objective. So inside of that, we have another expectation over S2, which is S2 given S1, A1, and that's also conditional. It's conditional on S1 and A1. And inside of that now we can put A2, then we can stick in R2, R of S2, A2, and so on and so on and so on. So you can rewrite this objective as a bunch of nested conditional expectations. And it has a very regular structure, right? You have this bit, S1 and A1. In here you can put R1. Then you have this bit, which is S2 and A2. Here you can put R2, and so on and so on and so on. So it's a very, kind of very recursive in nature. This still doesn't tell us how we can optimize theta. But now let's try to imagine that this block in here, basically everything inside the second expectation, maybe we actually know this part. Maybe we have access to some function that tells us the numerical value of R of S1, A1 plus this expectation, R of S2, A2 plus the expectation inside that, and so on and so on and so on. And we're going to call this Q. We're going to say we have this function called Q. It's a function of S1 and A1. And it just tells us this part that's inside. It tells us R of S1, A1 plus the expectation over S2 plus so on and so on. If somehow we can get access to this function, which is a function of two variables of S1 and A1, then this whole thing becomes just the expectation under S1 distributed according to P of S1 of the expectation of A1 distributed according to the policy of Q. So now if we know Q, let's say we know everything about Q. Let's say we know its derivatives, we know the whole thing. Does anybody have any idea about how we could choose pi so that it's better than our current pi? So my goal here is to pick a new pi of A1 given S1 so that it's better than the one I had before. Yes?
Pick the one that maximizes Q.
Yeah. Pick the one that maximizes Q. Remember, this is your objective. Your goal is to maximize this objective. I've just rewritten the objective like this. It's the expectation of this thing called Q. I want to make it as big as possible. So I'm going to change pi to make this thing as big as possible. So I can just pick the one that maximizes Q. So just to be concrete, which one is that? What is, can someone just tell me what pi should be in order to maximize this expression? It's a probability distribution, right? So you have to tell me what is, yes?
So it should be 1 if A equals R max of Q.
Right, so the answer was pi should have probability 1 when you give it the A that maximizes Q of SA, and it should be 0 otherwise. So it's easy to modify pi if pi of A1 given S1 if Q of S1 A1 is known. You just pick the one that makes this value as big as possible with respect to A and give it a probability of 1. That's not the only way to do it, but that's one really easy way to do it. Now, you have to be a little careful because your parameters, theta, might actually affect multiple time steps. So here I just assume that they're only affecting time step 1. You might have just made time step 1 better, but time step 2 much worse if your parameters actually tie things in time. So you have to be a little careful about that, but if we're just concerned with this part of the problem, it's very straightforward. So all that's meant to show is that if you know Q, it's super useful. You can, once you know Q, improving your policy can become much more straightforward. So let's define a few objects that are useful. So we already met the Q function. The Q function is formally defined. You can define it for any time step as following. So I'm going to put a little superscript pi on Q just to indicate that this is the Q function for a particular policy. So it's not a Q function for any old policy. It's a Q function for this particular policy pi. And the Q function at time step t of STAT is just defined as the sum of the expected rewards from this time step until the end. So it's the total reward that you will get if you execute action AT in state ST and then follow the policy pi in expectation. That's the definition of Q. You can also define another closely related object called a value function. The value function is just the state version of the Q function. In fact, sometimes the Q function is referred to as the state action value function, whereas this is just the state value function. So the value function is just the expectation of the reward that you will get if you start from state ST and then immediately follow the policy. So action AT is sampled from the policy. And of course, you can equivalently define the value function as the expectation of the Q function, where AT is distributed according to the policy. These two things are equivalent because of how I've defined Q. So these value functions and Q functions will come up very often in this course. And one interesting detail here is that the expectation of the value function at state 1 is the RL objective. Of course, we can see that because this is the definition of the value function. It's just the expected reward. So if you plug in t equals 1 and take the whole expectation of this with respect to S1, then you just recover exactly the RL objective we had before, which is the sum of the expected rewards at all the time steps. So what are some of the ways that we can use Q functions and value functions? There are a lot of ways in which we can use them, and also a lot of different ways that we can learn them. So one idea is that if we have a policy pi, and we know the Q function for that policy, then we can use it to improve pi. So this is basically what we saw before, where you just set your policy to give a probability of 1 to the action that maximizes Q. So you just create a new policy pi prime that gives a probability of 1 to any action that maximizes Q and 0 to all the others. And you can show that this policy will be at least as good as pi and probably better in many cases. And this is essentially policy iteration. It actually doesn't matter what pi is for this. Another idea is you can use Q to get gradients that you can use to then improve your policy. So maybe this argmax is difficult to do for some reason. Maybe there's a million different actions, or maybe the actions are continuous. You can also use your Q function to compute a gradient that you can then use to improve pi smoothly. There are a couple of properties that are very valuable for understanding this. So if you have some action A where Q of SA is greater than V pi of S, then this action is better than average. This is actually a very natural statement because V pi of S is just the expectation of Q under pi. So V pi of S is it's literally the Q value of the average action under pi. So if you have some action for which Q of SA is bigger than V of S, that is a better than average action. In fact, one quantity that we'll introduce later when we talk about actocritic algorithms is Q minus V, which is referred to as the advantage. And that measures how much better is this action than the average action. So you could, for example, modify pi to increase the probability of actions for which Q of SA is bigger than V of S. And that'll give you also a better policy. And if you do this locally, if you compute a derivative, then you can get a gradient-based optimization procedure out of this. So these ideas about how you can use Q functions to improve policies are very important in RL, and we'll revisit them again and again. The first set of RL algorithms we'll cover, which are policy gradient methods, actually don't use this, but later on we'll talk about value functions and actocritic methods, which will make very heavy use of these concepts. So value functions and Q functions will continue to come up again and again. Okay, so to review the first part of the lecture, I talked about some definitions, Markov chains, Markov decision processes, and their partially observed generalization, which is partially observed Markov decision processes. I talked about the reinforcement learning objective, which is defined in terms of the expectation of the reward. How do you evaluate expected reward? Well, there are a few choices. We'll cover many other choices later on in the class, but basically you have these nested expectations. We talked about the structure of RL algorithms, how there's these 3 blocks: sample generation, fitting a model or estimating the return, and policy improvement. And all of the algorithms will have these 3 blocks, and we'll see what they are later on. And then I talked a bit about value functions and Q functions. So now we're going to take a short break. It'll be about, let's say, 3 minutes. And then after we come back, I'll talk about how sort of the set of different RL algorithms we'll cover in this course fit into this scheme with the 3 components. So let's take a 3-minute break, and I'll see you all back here at 11:06.
So I talked to a couple other people too, and most of us implemented the policies as deterministic policies. Is that usually like a standard thing to do?
Right. So that is the standard thing to do, but depending on how you fit your policy, it's actually kind of equivalent to a particular stochastic policy. So you're fitting it by minimizing squared error between the predicted action and the actual action, right? So squared error, it's like pi of s minus a squared. This is actually very close to the log probability under a Gaussian. So you're minimizing this. If you maximize it, you put a negative sign in front, put a 1/2 here, and subtract 1/2 of the log determinant of your covariance, which we're going to say is identity, so it's just a constant. That's basically the log probability of a Gaussian with a covariance of identity. So it is like a stochastic policy. It's just Gaussian with a covariance of identity.
But then when you're actually acting, though, doesn't your network just output like a deterministic?
Yeah, you could sample from this if you want.
Okay.
In that case, it's usually better to not have your covariance be identity, because usually that's very large. That's a very noisy policy. But you could very easily do the usual thing of having the sigma inverse here, and then compute the derivative of this with respect to sigma and optimize that too. Oftentimes it's easier if you have a diagonal covariance, because then these log determinant terms become very simple. Yeah.
Okay.
Why model-based policy only handle the deterministic?
So model-based RL doesn't have to optimize deterministic policies. It's just that particular simple procedure I had on the slide optimizes deterministic policies.
Only determine no stochastic.
Oh, because it trains with backprop. So sampling is a non-differentiable operation. So you can't propagate gradients through it. There are tricks you can use to make that possible, and we'll cover these later in the course. For example, the reparameterization trick.
Yeah.
But yeah, regular backprop, assumes everything is differentiable.
And another thing is in last class you say about to the mixture of Gaussian, and how to use the neural network to produce that. It's just
right. So you can write down the log probability under a mixture of Gaussians in closed form. Yeah. It's a little bit ugly because you have like a log of a sum of exponentials and so on, but you can still write it down, and then you can compute its derivatives with TensorFlow, just exactly using all the stuff Greg covered before. And that's it, basically.
So the network only outputs the parameters.
Yes. Yeah. So it outputs. Let's say you have n mixture elements. It outputs n means, n covariances, and n weights.
Then you can calculate the probability.
Yeah. That's it.
Okay. Thank you.
Hi. I'd like to know if I could be added into this course.
Please come back after class.
Okay. Sure.
Do you have a quick question?
I have a question about notation. When you realize something like this, can you briefly explain what you mean by that?
It's the marginal of the trajectory distribution. So you have a distribution over all the states and actions, and you marginalize out everything except for the ones for the state and action at time t.
I see. So the probability that the state action time pair will occur sometime in the trajectory.
No, at that particular time.
At time t.
Yeah, because there's a sum over t. Yeah. I think I need to restart the lecture. Okay, welcome back. So in the last part of today's lecture, I'm going to talk about a few different types of RL algorithms, and I just want to give a summary of the ones that we'll cover in this course. So it's going to be pretty brief. Again, I'm not going to go into detail about the algorithms. I just want to give you sort of the table of contents, so to speak, of what we'll see in the next few weeks. So all of these RL algorithms will, in one way or another, be trying to maximize the expected reward. We'll see policy gradient algorithms starting next week, and policy gradient algorithms aim to directly compute the derivative of this objective. Now, of course, the real full expectation is in general intractable to estimate because there are a huge number of possible trajectories, so policy gradient algorithms will make a sample-based approximation to this and then compute the gradient. We'll see also value-based algorithms. These algorithms try to directly estimate the value function or Q function. They'll actually be trying to represent this with a neural network. And then from that, they will try to explicitly recover the optimal policy using that argmax trick that we saw before. After that, we'll cover actor-critic algorithms. And actor-critic algorithms are actually kind of a combination of these two. So actor-critic algorithms also estimate a value function or Q function explicitly by using some kind of function approximator like a neural network. And then, instead of directly taking the argmax, what they actually do is they use these value functions or Q functions to get better gradients for policy gradient methods. And there are a few appealing convergence properties there, so there are a few reasons why you might actually prefer to use actor-critic algorithms instead of directly recovering the policy from the value function or Q function. And we'll talk about that later on. Then, after we're done with model-free RL, we'll actually cover model-based reinforcement learning algorithms. So model-based reinforcement learning algorithms basically build on the basic idea that I presented before, where in the blue box you estimate directly which next state you'll see given the current state in action. Sorry, in the green box you estimate which next state you'll see given the current state in action, and then in the blue box you somehow use that model to improve your policy. And there are a number of different ways to do this. So you'll estimate your model, and then you can use it for planning directly, so you might not even have an explicit policy. All you learn is the model, and then use it to figure out how to act. Or you could use it to improve a policy, or you could use it to do something else. And there are actually quite a few different options for how you can use a model to help you make decisions, and we'll cover that in the model-based RL section. But today what I want to do is I just want to explain how each of these categories of methods fits into the basic anatomy of the RL algorithm. So for model-based RL algorithms, we basically already saw this before, but in the general version, in the green box, you learn some kind of model for P of st plus 1 given st at. Maybe you assume this model is deterministic, in which case you just have that f phi that we had before, but you can also actually learn stochastic models. So there are many different choices for how you structure your model and so on, but basically you would use your data collected in the orange box to fit a model in the green box. And then here you have a few options, as I said before. So let's dig into this a little bit more. Improving the policy for model-based RL algorithms, there are quite a few ways to do it. You could just use the model to plan. So what that means is you got your model up here, you pretend that it's essentially the correct model of the world, and then use your favorite planning algorithm that you maybe learned about it in your artificial intelligence class, or if you covered some kind of search algorithms, a lot of those could be used there. You could also use ideas from optimal control here. So you could use, for example, trajectory optimization algorithms, optimal control algorithms. These primarily are designed to work in continuous spaces that are basically going to use derivatives from the model, essentially back propagation to optimize over actions. And there are a few different ways to do that also. In discrete spaces, in discrete state and action spaces, we'll actually cover an algorithm called Monte Carlo tree search, which is a particular search algorithm that's pretty popular in reinforcement learning, but there are also many other choices there. You could use your model together with a policy to backpropagate gradients into a policy. The very kind of basic naive version of this that I had before the break often doesn't quite work, but there are a number of tricks that you can use to make it work better, and we'll cover some of those tricks. And you can also use a model to learn a value function, and then do all the stuff that we would ordinarily do with value function-based methods. So this is, you can, for example, do dynamic programming, just like in regular dynamic programming methods for MDPs, but using a learned model. You can also use your learned model to generate simulated experience, and then use your favorite model-free algorithm to learn the value function. So you can literally just plug in another algorithm like a policy gradient or actor-critic or something like that into a model-based method, and just use the model to generate fake synthetic experience. And this class of methods is sometimes referred to as DYNA. So if you hear someone say, oh, I'm using DYNA, what they mean is that they learn a model, use that model to generate synthetic experience, and then plug that into a model-free learner. Okay, so how about algorithms that use value functions? So not model-based RL necessarily, but algorithms that use value functions. They're going to be using the data they collect in this orange box to fit the value function or the Q function. So remember, the value function and Q function are estimates of these expectations. Of course, you can't measure the expected values directly. What you measure is samples. So you can estimate an expectation by an average over samples, and you can use those sample averages to supervise the value function and the Q function and train them here in the green box. And once you have value functions or Q functions, you could do something very simple to recover a policy, like what we discussed before, is you could just simply set your policy to be the deterministic policy that outputs the argmax of Q. It's a policy that assigns a probability of 1 to the argmax and 0 to everything else. But there are also other ways to do this. With direct policy gradients, this is actually something that I alluded to before. Your blue box is just going to apply the gradient of the reward function, of the expected reward function, to theta. And computing this gradient is a little bit tricky mathematically, so that's what we'll cover next week. It actually doesn't require knowing the derivative of R. It only requires knowing the derivative of your policy, which is kind of neat. And then there isn't really a model or an estimate of the return. It's just a sum. So you just sum together your rewards, which is all you're doing in the green box. And then actor-critic algorithms combine these two ideas. For actor-critic algorithms, they're going to fit the value function or the Q function, just like with the value-based methods. But then, to improve the policy, they'll actually use the value function or Q function to get a better gradient. So basically, this box is like in policy gradients, and this box is like in value-based methods. OK, so there are a bunch of different reinforcement learning algorithms, and I sort of went through the table of contents, and we'll learn about each of them and so on. But maybe one kind of obvious question as we go through this whole process is, well, why do we have like a whole bunch of different methods, and why do we have 3 to 4 weeks of this course dedicated to just the model-free ones, covering each of them in turn? Why isn't there just one thing that we can just pick up and use all the time? The reason for it, of course, is that there are many different trade-offs between different reinforcement learning algorithms. And depending on the assumptions of your problem and the particular demands of your problem setting, whether your data is expensive or not, whether you have a lot of compute or not, and so on, different algorithms might be preferred. So that's why in this course we actually cover many different algorithms. So what are some of the trade-offs between different reinforcement learning algorithms that we need to be aware of? Why are there so many RL algorithms? Well, different RL algorithms will have different degrees of sample efficiency. So when I say sample efficiency in this class, what I mean is how many samples do you need to achieve a particular level of performance. So if one algorithm can get to a reward of 1,000 using 1,000,000 samples, and the other one can get to a reward of 1,000 using 1,000 samples, that second one is a lot more sample efficient. Different algorithms have different trade-offs as far as stability and ease of use. So the term stability is sometimes thrown around very informally in reinforcement learning. It doesn't actually have a very clear definition when we say my algorithm is stable or unstable. But colloquially, what it refers to is how frequent, like if I run my algorithm some number of times, how frequently will it actually converge to a good answer? And how carefully do I have to choose the hyperparameters of the algorithm in order to get it to converge to a good answer more frequently? And so this basically refers to ease of use. If your algorithm requires a lot of manual tuning to get it to actually run, then it might be very hard to use. If it just works straight out of the box, then it's very easy to use. Different algorithms also make different assumptions. So maybe some algorithms will assume that your dynamical system, your MDP, can be either stochastic or deterministic. Some will assume that your policy can be stochastic or deterministic. So depending on which of these assumptions fit your problem, that might inform your choice of algorithm. Some might assume that your state space or action space is continuous or discrete. So there are, of course, a few choices there, and you have to make sure that that fits your assumptions. And some will assume that you have episodic MDPs, and some don't care whether you have infinite or finite horizons. And then lastly, different things are easy or hard in different settings. So sometimes, depending on the particular details of your problem, it might be easier to represent a policy than it is to represent the model. For instance, in the real world, if you have a physical robot interacting with the world, maybe the laws of physics are very, very complicated. But the particular behavioral strategy that you need to perform your task might be very simple. Or you might have the opposite. You might have an environment where predicting the future or modeling the world is very simple, but the behavioral strategy that emerges from that might be very complex. So depending on which of these things is true for your environment, maybe it's easier for you to learn a policy, or maybe it's easier for you to learn a model. And this depends on your problem. So let's start by talking a little bit about sample efficiency, because this is often an important topic, especially if you're concerned with settings where you don't necessarily have access to a very fast, very efficient simulator, which is maybe one of the reasons why you might want to use reinforcement learning, if you want to learn directly on your system. So sample efficiency is how many samples do we need to get a good policy? And that basically deals with this orange box. So one of the most important questions in practice, if you want to determine whether a particular algorithm is a good fit for you in terms of sample efficiency or not, is whether it's an off-policy algorithm. There are many factors that affect how efficient an algorithm is, but whether or not it's off-policy is one of the more important ones. So let me explain what that means. So off-policy means that your algorithm can use samples to improve the policy that were not necessarily generated with that policy. Let me explain the two alternatives here. So the opposite, on policy, means that each time the policy is changed, even a little bit, you have to generate entirely new samples. And in practice, this leads to very different degrees of efficiency, because of course, if you have to throw out all of your old samples each time your policy is changed, then you're going to probably need to generate a lot more samples overall, whereas if you can reuse past samples, then you can be more efficient. So, for example, policy gradient methods, conventional policy gradient methods, are on policy because they use the samples to estimate a policy gradient and then throw out those samples and collect new samples from the updated policy to compute a new policy gradient. This makes them very simple and very easy to use, but more expensive in terms of samples. And in general, we can kind of crudely, at a high level, put all these different categories of algorithms onto a continuum between the most efficient and the least efficient. And somewhere here on that continuum, there's going to be a dividing line between off-policy algorithms and on-policy algorithms. So generally, some of the most sample-hungry, some of the least sample-efficient algorithms are going to be methods that are based on gradient-free optimization. So if you've heard of things like evolutionary strategies and so on, they're going to fall over here on this end. On-policy policy gradient algorithms can be a bit more efficient, and they're somewhere over here. And then actor-critic-style methods fall somewhere in between. And some actor-critic methods are actually on policy and some are off policy, depending on the details of the method. There are a lot of very popular off-policy methods based on directly learning Q functions, Q learning being the most well-known one, and they tend to be a bit more efficient than the actor-critic methods if used properly. And then you have model-based RL methods, which are a bit more efficient than that. And then model-based methods that are not based on deep RL can be even more efficient, but of course are difficult to apply to very, very complex problems where shallow models don't give you accurate estimates. So from looking at this kind of continuum, you might say, well, why would you even use less efficient algorithms? Like, isn't more efficiency always better? Like, shouldn't you always use the stuff here on the left and just forget about the stuff over here? But of course, sample efficiency isn't the only dimension that matters. And one kind of somewhat surprising but generally true fact is that wall clock time, the amount of actual time you need to wait for something to run, if you're using a very cheap and very parallelizable simulator, it's not the same as sample efficiency. In fact, it's often almost the opposite. So part of why evolutionary strategy type algorithms are a thing that people use, and part of why on policy gradient algorithms are popular is because if you have a cheap simulator that you can parallelize, it might actually be faster in terms of actual wall clock time to do things over here using massive parallelism than to do the more efficient stuff over here, which requires less samples overall, but perhaps more compute or might be harder to parallelize. There are other trade-offs also. So, and another one of the trade-offs that's also often a big deal is stability and ease of use. So, one of the most important concepts, one of the most important questions in regard to stability and ease of use is this question: does the algorithm converge? And another question is, if it converges, what does it converge to? And does it converge every time? Now, you might kind of wonder, seeing these questions, if you took a class on optimization or machine learning, you might be asking yourself, well, why is this even a question? Like, why do we ever care about algorithms that don't converge or algorithms where we don't know what they converge to? This just seems like a disaster. Why is this a thing? So in supervised learning, you're almost always doing gradient descent if you're doing deep learning and supervised learning. Or if you're not doing deep learning, you might be doing something that's even more well-behaved than gradient descent. You might have some sort of convex optimization problem, which is even easier. So in supervised learning, we almost never ask these questions because the answer is yes, it converges to a local optimum, and it converges every time. Done. In reinforcement learning, unfortunately, things are often not so simple. Many reinforcement learning algorithms are not gradient descent. They might compute things that look like gradients, but they're often not actually doing gradient descent on the reinforcement learning objective. So Q-learning, which is where you learn these Q functions, typically is not actually doing gradient descent on the expected reward objective. It's doing a kind of a fixed point iteration, which can converge under very simple function classes, but generally is not guaranteed to converge for complex function approximators like neural networks. Model-based reinforcement learning is doing gradient descent to optimize the model, but optimizing the model is not the same as optimizing the reward. So when you try to fit the best model to your data to predict ST+1 given STAT, that is gradient descent. It's supervised learning, in fact, but it's not explicitly trying to maximize the reward. It's trying to get you a more accurate model. And while more accurate models oftentimes will lead to better policies, they're not guaranteed to do so because some errors in the model might be much costlier in terms of reward than others. Policy gradient is actually a gradient descent, or actually gradient ascent procedure because it's a maximization, but it's also often the least efficient. So while it does converge and converges to a local optimum, it can require a lot of samples to do so. All right, so let's dig into these a little bit more. Value function fitting. When you fit value functions, usually what you're minimizing is the error of the fit, meaning how close is the value outputted by your value function to an estimate of that expectation. But matching that expectation very closely is not actually the same as producing a good policy. Of course, if you match it perfectly, if your error is 0, then you will get a good policy. But if your error is not 0, those trade-offs don't necessarily translate into equivalent size changes in expected reward. So it's not the same as expected reward. And actually, value function fitting, the way that it's typically done, at worst doesn't actually optimize anything. And in fact, there are counterexamples that show that it can diverge. And in practice, there are a bunch of tricks that you can do to make it converge more often, and we'll cover some of these in the class. So many popular deep RL value fitting algorithms are actually not guaranteed to converge to anything in the nonlinear case, but there are a bunch of kind of heuristics and tricks that we can use in practice to stabilize them. But it's still very much an open question in reinforcement learning as to how to derive effective and convergent algorithms of this category, and currently there isn't a single good answer to that. Model-based RL, the model minimizes the error of fit, as I mentioned before, which will converge, but the convergence of this part is not guaranteed to give you actually a better policy. And then policy gradient is the only one that actually performs gradient ascent on the true objective, which does make it actually, in practice, often much easier to use, but it has a few other issues like high variance that we'll talk about. Comparison about assumptions. There are a few common assumptions that are made by some algorithms, but not by others, and these are good to be aware of. So I'm just going to list the more common ones because these are the ones to watch out for. So some algorithms will assume that you have a fully observed system. So remember that we can train a policy that's based on observations or ones that are based on states. Some algorithms assume that you have states, not observations, meaning that they satisfy the Markov property. So that's the distinction between, the cheetah is always there, but when the car drives in front of it, you might not see it, but of course it's still there. So the state hasn't changed, but the observation isn't sufficient to deduce it. Generally, this kind of full observability is assumed by value function fitting methods. So methods that directly fit a value function or a Q function implicitly assume that you're actually giving them a Markovian state. You can mitigate this issue by using recurrent value functions and Q functions, so not all is lost if you don't have a Markovian state, but this is an important thing to keep in mind, especially for value functions and Q functions. Another common assumption, episodic learning. So episodic learning means that the learning process is structured into repeated finite horizon episodes. So here's a video of a robot that's doing episodic learning. So what it's learning to do is stack this Lego block, and you can see that it moves its arm back and tries again over and over again. So each of those trials is an episode of finite length. Not all problems are episodic learning problems. If you have, for example, an algorithm that's doing stock trading, maybe it's just running in real time in the real world, like the world doesn't reset to the year 1990 every single time, you just keep going and going and going. So that's not an episodic problem. But some problems are episodic problems. So oftentimes episodic learning is assumed by pure policy gradient methods, although actor-critic methods can remove this assumption. And it's also assumed by some model-based RL methods, but not others. And then a third common assumption is continuity or smoothness. So continuity or smoothness means that your dynamics are continuous, or maybe that your actions are continuous and smooth in the state or something like that. So this is often assumed by some value function learning methods. We'll cover things like deep deterministic policy gradients that make an assumption about smoothness. And it's much more often it's actually assumed by model-based reinforcement learning methods. So for model-based RL and continuous systems, assumptions about smoothness are something to watch out for. Okay. So just in the last couple of minutes, what I want to do is I want to give you a few examples and a few videos. So I'll skip over this thing and just go to the videos. So here's one example of a reinforcement learning algorithm. This is something that some of you might have already seen before. This is the work on playing Atari games by Ni et al., which used an algorithm called Q-learning with convolutional neural networks. So this is an example of a pure value function-based method. In this method, they directly learn a Q function and nothing else, and then actions are taken by simply maximizing that Q function. So the actions here are the buttons that you push in the Atari game, so there's a small discrete set of actions, which means that you can evaluate the Q value for every single one of the actions, and then pick the best one. And then this algorithm learns to play various Atari games. Here's an example of a model-based reinforcement learning method. This is an algorithm applied to controlling robots. So this is the paper, and this is an algorithm called guided policy search, which is a type of model-based reinforcement learning that we'll cover later on in the class, which is based on kind of an episodic learning setting where the robot attempts a task multiple times, fits a model, and then uses that model to improve the policy. Here's another example. This is a little simulated robot learning to walk. So it falls repeatedly over and over again until it learns to run faster and faster. So this is from this paper by John Schulman et al. And this is showing an algorithm called trust region policy optimization, which is a policy gradient algorithm. But in this case, it's actually also combined with value function approximation, which actually makes it an actor-critic algorithm. So we'll cover actually this method later on. And here's another actually very recent example. This is an algorithm called Qt-opt, which is a type of Q-learning algorithm, actually quite similar in nature to the one that I showed before playing Atari games, but here it's sort of a special made for these robotics applications where there's actually a continuous action space and the robots are learning to pick up objects. So the robots control the motion of the gripper and they're trying to use image observations to figure out how to most successfully pick things up. Okay. That's it for today's lecture, and then I'll see you all on Wednesday for policy gradients.
Question about the